So good evening all. Uh, my audience. Okay, let's uh, start our second live session. So as usual, we are going to solve some questions. So let's start with this one. So this particular question. Wait, first question. We have given is this particular symbol. This is for recyclability. So, and for this particular thing, they want to know for which type of polymer this sign is given. So, the answer is actually polypropylene type polymers for that. This thing is given. So, if we look into a bit detail, so let's go to the structure, the lecture slide. So there it is, uh, 31. So, it's explained. Uh, So, that uh, that plastic or films, poly this particular this kind of polymer. So their consumption from 1950 to 2020, this you can look at that. It's almost to 10 billion metric tons. So huge amount of this particular polymer is being used, and they obviously going to generate a considerable amount of wastage. For that, this recycling thing is very much important, and for which polymer or plastic that recyclability is good, and that is considered as uh, better option for this kind of thing. So if we look into the waste, so here you can see that plastics are everywhere, right? So they cause a lot of pollution also, and these things are new. Now, for the recyclable polymers, so there are various symbols like this. So this is for PTFE, uh, and this is high density polymer, and this one is for low density polymer one, and that given question that polypropylene one, that is five. This one. This is uh, actually given. So that's how the numbering are, and PVC is this three, which is symbol as three. These are the some six, so six options are there, uh, and in that way they are actually identified. So thermoplastic and thermosetting polymers. So in previous class we have already learned about this kind of things. So thermoplastics, when you heat this kind of molecule, they soften and can be reformed when used, but for thermosetting polymers, when you heat the hardening is skill. So that thing we have explained why, because for thermosetting polymer, they are between different macromolecular chain or polymeric chains, you are going to form some chemical bond. So that's why when you are doing that thermosetting polymer and you heat it, so you can see hardening of hardening. You can for thermoplastic ones, so they are only minerals which are responsible for different polymeric chain units, and there are no such kind of uh, chemical bonds are there. So that's why when they are heated up, so they melt or something. So these things are observed, and according to this different property, when you heat this kind of polymer, these two actually, that's how this two things came, thermoplastic and thermo. So here you can see some of the uh, materials that in our daily life that are used. So polypropylene pipe. So here you can see this kind of thing are there. So this kind, so this some examples for this kind of materials that are used in day-to-day life, and yes, they are harmful for environment, but obviously essential also now. So for this these things are there, you can see the structure. So according to the monomer units, the structure is different. So this is nylon and the polypropylene. So the propylene unit is there, and that is the repeating unit, and this polyether. In that way, many polymers are there. So now coming to our discussions. So now coming to the next question. So here we ask about this. So which principle of law states that in equilibrium process the semi-intermediate and the transition state are encountered in the forward direction, and the reverse direction comes so in the opposite direction. So the principle of microscopic reversible, so that reversible reaction we are talking about, and they just want to know the which principle it classified with this kind of definition we can say. So this is the principle of microscopic reversibility. So if we come to the thing that it comes from, it's also described. So go to that let's just it is here I think. So when this particular thing is so let's just discuss a bit. So tandem dehydrogenation and olefin cross metathesis, so TDOCM. For this kind of reaction, what happens is breaking of non-polar bond in polymeric cycle. So if you have this kind of polymerization, so uh, uh, this thing can be reversible with this particular condition. So if you have this kind of double bond, so here we have unsaturation. Now with hydrogen mediated reduction, we can just saturate the whole system and make it as this kind of completely saturated alkane system. And reversible reaction is also possible if we can do the oxidation. Let's say here azote and here H2, they can be also taken up, and we are just doing one level of oxidation over here. And with that dehydrogenation, you can generate back starting material or then double. So this process can be reversible with some particular reaction condition. So from here, we can actually do that olefin cross metathesis and followed by hydrogenation. So that just we are going to see how it is happening. So let's say if you have this kind of polymeric chain, and in presence of which this iron-based, sorry, not iron, iridium-based catalyst or reagent, so this particular thing can be used, and they are dehydrogenation of so that take one that hydrogen from the molecule. So here you are seeing so here there is no hydrogen, and after this iridium to iridium H2, so this thing happening, and this is the structure of them. And so there are many uh, uh, reported ligands are there like this. So this particular position can be very this particular position they can be varied with like a butyl group or hydrogen with what they can be varied. So they are generally hydrogen, and this with the phosphorus the ligand that is attached, that is tertiary butyl. And for this case, same thing. So this is there, and sometimes isopropyl and here OAB methoxygroup they are also used. So these are the some variants of this particular ligand. The main role of this particular ligand is it can capture one hydrogen molecule from your system, and so basically it's doing oxidation over here. So after that thing, you are going to generate obviously that double bond like this, and then so two units can be made actually. So here, let's say you are giving hexane from like alkane, and here long chain unit is here. And after this catalyst, so both oxidation would be happening. So here you are generating hexane, and here that's unsaturated polymer. Then cross metathesis happens. So first metathesis, you all know. So in just after 2 3 slides, I think I am going to discuss about that also. So cross metathesis. So here you are seeing that. So this part is attaching with this, and the another part is with this one. So that's how that cross metathesis is happening. So mechanism you are going to. So here you just focus on how this thing happens. So after this, these two units are generated like this. Then now that iridium catalyst that captured hydrogen, now this can be your hydrogenation reaction like this. So that hydrogen that is attached to iridium, it can now reduce your polymer chains like this. And again, it generate these two type polymer. So and this way the cycle repeats. So that's how this tandem dehydrogenation and metastasis happens in presence of this iridium atoms. Not only iridium, this molybdenum-based catalyst also used for this metathesis. For hydrogenation and dehydrogenation, iridium catalyst, and for metathesis, this particular molybdenum-based reagent is. So again, so the same thing. So this is for one particular example they have shown. So with this hexane and this polymer unit, this thing happen with this. So here that long chain is present. Then isomerization and metathesis is the same way that we have this. Now coming to the first thing, this thing they have asked actually. So with this metallocene catalyst, so polymer is generated. Now when that this kind of thing is used, so uh, some this kind of products are formed actually, degenerated products to actually create. So this thing happens when this particular state is reversible. So that's why this particular term came, or in this context, microscopic reversibility came. So this was proposed in 1924 by Richard Tolman, and it says that at equilibrium, any molecular process and reverse of that occurs on the average at the same state. So the same state actually. So this that molecular process and reverse process simultaneously happening. That's is the thing, and that transition state for each mechanism are identical regardless of that reaction direction. And accordingly, the reaction path in the reverse direction must be uh, in every detail be the reverse of reaction pathway. So in the forward direction. So here you can see one of the examples. The equilibrium process that intermediates and transition state are same for these cases. So here if you see So when we do the forward reaction, so for this particular case, so in presence of acid, what happens? It can generate this kind of tertiary carbocation. And then H2 is there, so it attached here like this and it generates the uh, tertiary alcohol. This is the forward part. Now in the reverse, in the opposite direction, what should happen is completely reverse of that. If we again charge this with H plus, will be get intonated, and with the same intermediate it will like this. Here you can see the identical thing. Then again carbocation would be generated followed by elimination would be seen. So here you are seeing that forward and backward. So these two pathways are completely uh, dif- uh, will completely reverse with each other in, in terms of atom connection and disconnection mode. Connection disconnection completely reverse like this. And the, uh, the intermediate we are forming is for the tertiary carbon. So that's the principle of this kind of that's reversible microscopic reversible. And for this case, we are also doing the same. So with iridium, when we are doing that hydrogenation and dehydrogenation, so they are actually just reverse phenomena with each other, and they are doing the that reverse thing, and the intermediate is there. So now coming to this, this is just energy diagram, and so this is the example. So here you are seeing that with HBr they have explained the same phenomenon. For electrophilic addition, so at first protonation like this, in this way, then carbocation generation followed by Br minus can attack like this, this is forward packet. And what happens in the reverse one? In the same way it would happen. At first, Br would try to get uh, this bond actually would try to get broken, and in that way transitions it would be forming followed by carbocation, and again then this uh, carbon hydrogen bond would be broken off. So in this case it is formed and here it is broken. And again the transition state is actually the same. So two transition state you are seeing is these two and these two, they are actually same for that reversible for that forward and backward reaction. That's why this particular example they are like they have actually specified like this. So in terms of kinetics, so if we see this particular equation, A plus B to AB, in equilibrium, you can say this kind of thing is there, and this actually describe like this particular relationship which is reciprocal. So this is the equation for this kind of uh, reversible reaction. Now for polyolefin degradation with California. So this particular principle actually affects. So that's why this thing is explained like in that way. With zirconium based catalyst at first, this kind of pi would be attached to your zirconium. So then insertion with alkyl transfer, this kind of thing would be happening, and this zirconium would be coming over. Now if we see that particular mechanism. So with zirconium, here you can see how it's been good. So with zirconium based iodide like this, at first it's attached with your olefinic chain, not olefinic, alkane chain like this way, and uh, followed by, so it is that pH activation you can say. In that way, this thing is happening. Then yeah, double bond is forming like this beta hydride elimination kind of a, so here not hydride is eliminated, but alkyl ring which is there, it is actually sequenced like this, so that you are generating that olefinic part towards here. Then that uh, uh, polymeric chain is transferred. So this one flip with hydrogen and this, these two things are generated. So the this particular carbon and zirconium bond is broken off and zirconium hydrogen bond is like. So then insertion happens from here. So this reduction is the references and again followed by this thing with this thing. This kind of thing. And that's how degradation of polymer happens with zirconium based pattern. So that's the way to actually recycle your material because in that way you are leaving that polymerization and again you are going close to that polymerization. So in that way you can say this process is your microscopic reversibility because in polymerization how we are actually making polymer by attaching one by one unit and with zirconium based this thing it is actually doing the reverse. So one by one unit, another unit is actually breaking this following this pathway and is actually degrading your polymer and which is needed for that recyclability of your polymer. So in that way, this thing happens and this is so these are the ligands for her attached with zirconium. So this kind of biphenyl based the case system what you have seen earlier that uh, sandwich type molecule is has used, but here it is sulfur so that it can break the polymer. One of the example of that with zirconium and this aluminum based species in presence of this unit, it can break that break your polymer like this. This get the special pathway with aluminum how it is happen. It happens. But first, aluminum and zirconium react and have this kind of species with your protein unit. Then beta hydride elimination leads to this kind of things. Uh, and these actually reacts with your polymers and have done by insertion reaction followed by the alkyl elimination. The kind of same process what we have explained earlier, and aluminum just catalyzes the whole process actually and sharp listening. And this is how uh, you can say that depolymerization can happen. In that way, depolymerization can happen. So ultimately it can give you monomeric unit and so it is do the recycling. So now coming to next question. So this one we have just explained what this is used for. This is dehydrogenation, right? This was for hydrogenation. The catalyst was let me write it. So here that methoxy unit, so that particular polymer they have region. So here we have propyl unit. So this is after taking that hydrogen from your alkane chain. Okay. So this can actually donate this hydrogen. So it is best. It can do the reduction. So this one is used for your hydrogenation. Mm. This one is used for your the hydrogen because there is no hydrogen, so you try to take hydrogen from the system like this, and here you are going to generate that olefinic fuel. This is used for your the hydrogen. Right. So the type of reaction they want to. So here that with static concept became so you can just discuss the metathesis part and again we use progress to this particular question. So let's start with metathesis reaction. So let me start. We can say general schematics for this kind of metathesis reaction. So if we see the how the name this metathesis name. So from Greek word meta, it means change and thesis means position with changing position. This particular name is given for this particular phenomena or mechanism. You can say that metathesis. So it is actually exchange of two parts of two substrate. So if you have like this kind of connectivity AB from CD, for metathesis you are going to see AC in BD. This kind of exchanging of strings we have. So other possibilities obviously there AD and CD. That's also can be studied. So these two are four and the possibility of metathesis. So here B change position with your C and the vice versa. So through carbene exchange between two starting molecules, this thing actually forms. So it's actually popular for this kind of polyphonic unit like this. Here you can see that R1, R1, R2, R2, and this. And when it with catalyst, what happens? This part it attached to this one, and you have this kind of system and R2, R2, and R2. They combine with each other. You have this kind of. So if we see the mechanism, this kind of uh, carbon-based metal or catalyst is used for that. So at first, what happens is this particular carbon can react with any of molecule, right? So let's say it is starting hot gas. So this is your first substance. So this R1 and your uh, carbon two kind of two plus two you can see not concerted way, obviously in stepwise manner, but the outcome is this kind of four members are metal are ring and you have this particular insert. Now here what happens? Uh, this bonds before me and this should be split. So in that way, you are going to generate this kind of carbon. So it is obviously a carbon, but here it is TH and here it is THRO. So that's how these two units actually change interchange is happened like in that way. And here you have generated one ethene gas, ethene unit which is liberated from this particular reaction. So after that, this part can again react with another unit of your alkene, like in that way, and again it will generate kind of intermediate followed by alkene. This this would lead to formation of this unit. So it got recycled back, and again that catalytic cycle can continue like this, and you have end up with this particular product. So here you are seeing in terms of AB. So this part and this part touch with each other and form this particular. And this part and this part again, they are also attached with each other and they have this particular unit is removed from the system like. Hmm. So So this is the general defense mechanism for your uh, data system. Now, this particular phenomenon actually in the Nobel Prize, so by graphs and chalk, so they won the Nobel Prize for the particular metaphysics type reaction, and they are actually in this kind of schematic extent for general public actually. So they are they have discussed or explained it, this kind of pair dance here we can say so this is your catalyst and this is one unit and this the other unit. And at the end you are generating not at the end in the intermediate what you are generating having four so one metal and three carbon center like this with the four member metal intermediate is forming and followed by that exchange what is happening. So here catalyst is attached to it is a green one, but there you are seeing that catalyst is now attached to the red moiety and this blue green ray joined with each other. So in that way, so in that context actually they have explained this particular phenomenon. So this is the example of rock carbon. So before coming to let me see, uh, for it's the general formula for short carbon and this for this kind of short carbon, this kind of uh, this is like molybdenum, tungsten, they are actually used and that are they are actually R and A are so they are bulky substituent for this kind of thing. So this is the commercially available short carbon where molybdenum is F uh, that metals in this particular center. And this is for the graph. So for graphs, it is generally ruthenium based molecules like this. So this is the one of the early catalysts what he have defined. So in 1992, so followed by first generation graph catalyst with this and now second generation is also available. Just mm, having more bulkiness over this particular thing. When here you are seeing that carbon unit for this the thing is attached to it, your thing. So these are some variants in each C hydrogen in heterocyclic carbon. So that is also used acetic acid and this is actually your second generation Lux catalyst. So these some of the examples. If you use this particular thing, like this, so this is how that's how the first generation graph catalyst they have made. So with this cyclopropene and presence of this ruthenium based reagent, these rings actually open up and this, this is generated which is that your graph catalyst. And so there are other ways also to make that with ruthenium chloride and this as a compound, again, this thing can be followed and you can make the first then economic catalyst and for the game generation. So with this particular thing, with this in heterocyclic carbon in presence of base, uh, this thing can is also reported. So, with base, here you are going to generate the carbon one as it is acidic proton. It would be taken up potassium hydroxide, and here you have minus, followed by that neutralization will lead to formation of carbon. And when this in heterocyclic carbon is formed, this phosphorus-based ligand would be flipped from your ruthenium center, and here you have that carbon ruthenium. This carbon thing would be formed. So now, looking into the variants, so these are some of the general metathesis what happens in your reaction. So let's look into that. This is the general, we can say, uh, option for what that metathesis can do. So cross metathesis, what we just have in that first exchanging uh, these two groups. So these should attach to your R3 and these these should be attaching with your PhD. Just cross metaphysics. So simple thing. What we have now. Coming to ring closing metaphysics. So for this, what happens? So let's say in the terminal position you have this kind of 12 things, and you need to you use this particular for or any of the carbon. So what would usually be happening is it would generate this kind of intermediate. Now, the same thing would happen like this. After that, you are going to generate this kind of unit, and again this thing. Now, so here you are have seen that now you have generated this particular object. So now that ring is initially a pen chain with this particular catalyst, it actually makes a ring over here. So in this particular mechanism, and so that's why it's called actually ring closing method. And another possibilities are the polymerization with this. So if so it is actually intramolecular. Intramolecular reaction happens, it goes to including if inter means, with other alkyl units, it can react. Then you can see the formation of chain units like this. So that thing would be called as uh, cyclic diene metacyclic polymerization. So with the same catalyst, these two phenomena can occur, and it can give you different. The short form for this is ADME, acyclic diene. Here you have diene acyclic and polymerization. That's the that name. Yeah. Now coming to this one, so this is called ring opening method. So if you have this kind of uh, the ring where you have that olefin unit, so it's using different catalyst, you can open up the ring. So let's see how it can happen. So let's see you have this thing and it reacts with the carbonyl. Now after that, you are going to generate this particular molecule or this particular intermediate. Now this can again happen. Now here you have seen particular bond is split like this. Now this part can react with another unit or react in the same way. And polymerization can go on like, and that's why it is called opening metaphase polymerization. So enzyme based, sorry, not enzyme, so that enzyme based synthesis also happens. So not only double bonds, if you have triple bond and double bond, again, same thing can occur. So, and you can end up with this kind of thing. So for this, if we see the mechanism, that's the same kind of metal metal carbon would be forming. Then it will react with your triple bond like this, and we have intermediate over here. We have generated this particular thing, and here uh, uh, really what happened is there you have generated this particular uh, R1 R2 this solution. Now this can react with this specific R1 R2. This and responding to this. Kind of way it will occur. So here you have generated that olefin unit and like this, and that carbonate is regenerated. That happened. So that's how in ion metathesis can operate. So for reopening cross metathesis, so what happens initially, you can consider this particular thing. We had after reopening in the terminal position, we are generating that metal-based active center, and now it should react with your particular olefin. So then cross metathesis. So that's how that combination of these two actually uh, ring opening metathesis and cross metathesis. This particular phenomena is also observed as ROCM ring opening cross metathesis. Now, for synthesis, if we see some of the examples, so in various uh, fields, it is actually used only in uh, polymeric industry and plastic, this kind of materials for synthesis of natural products, drug, this then also used. So for this uh, phenol molecule, that you can see, actually not difficult. So this one of the code of uh, code for that particular this kind of molecule. So they are first not this particular group in early days, they have used this particular closing method strategy to make this particular seven-member ring. So what they have done, they have started with this kind of epoxide and uh, with steps they have synthesized this particular molecule where you have this uh, polyphonic this terminal chain and with uh, research with rock carbon, they have able to make this particular seven member mechanism is clearly simple. So that first you are going to form a four member ring. So now that thin molecule would be removed from your system and you are going to have followed by the mechanism. We're going to make that one carbon bond here and end up with this particular estimate member. And that's how they made particular this seven member. And so for making this particular actually by Grab's metastasis reaction, they have done that. For example, for formation of this carbo analog of sulfide decatran. So here you are seeing with the graph with the generating. Let's count that. So one, two, in Lombardy, where you are seeing, they are able to do that in with that graph. So in general, this other conditions, basically making this particular big ring is not very much easy. So with graph catalyst, they have able to do that with 60%. So here, so this is the terminal change, and they need to be uh, chain up this particular carbon, this carbon. For that, the same strategy can be used with this one for mm, rock carbon, and this is graph. With graphs chain of catalyst, they are able to hold that. This is an example of one graph uh, is closing metathesis. So this is the terminal unit, and they can be joined like this in presence of particular chain one. We have got up to 50%, and so this one is done by call it phase synthesis by Nicolau for their synthesis of isothiolone A and its various derivatives. This particular uh, ring closing metathesis and Libre's strategies which uh, shown was shown by by that Nicolau. This is example of you can say that cross metathesis with allylic stereo control manner uh, by the allylic amine. So this allylic amine, uh, they have here we have seen with 97% enantiomer each product they have started use that particular admin and with this uh, silicon-based machine unit using for the other parts. And again, they are using here that's your soft carbon, molybdenum-based carbon. So with that they have seen to have that cross metathesis reaction. So this unit and this unit they have fully able to couple, and this is obviously going to be the byproduct in molecule, and they have only seen p isomer to be forming, no p isomer is forming, and it's meant to be 20 and 90% in isomeric acid. Uh, they have done this particular cross metathesis. For this one again, one of the examples for cross metathesis, uh, 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 and with tidal catalysis, they are able to do that, and this was developed by Fenda and Schwarz group. The Schwarz carbon obviously molybdenum one is used, but Schwarz is involved in this particular project, and that's weekends that we are using are tidal. So here you are seeing that binol means uh, reduced version of that strip type thing they have used as design over there. And here this caption finally. So this is actually uh, responsible for your nantiomeric uh, excess that they are getting 98 and 98%. For that thing, they are using this binary trip-based reagent, not binary uh, reduced version of. So the use of this, they have got that high non-shimmery and products are predominantly trans due to that stability result, and they have got uh, also 56, 57 this kind of we look into the mechanism. Let's see how it is happening. Uh, bond is critical. Let's see how. So, inertial selectivity is obviously due to this presence of this binary units. How the mechanism is happening? Let's one you I want to explore. So, phenomenal system are there. So, at first, uh, kind of activation will be there, and followed by ring opening, I guess. So, where is this unity? In it means that five. So now we when up this, we have that this kind of thing. You have this like OBN, and there you have one group. So, this, you know, this part and the attachment. So here you are seeing that the exterior selectivity is inherent, we can say. First, this OPN and these two bonds is already fixed in this particular molecule. So what happens? So the stereochemistry of this carbon cannot be affected because they are not participating in the reaction mechanism. So that inherent properties maintain that all are seen actually it be happening. So here you are seeing all are seen. Financial liquidity is driven by that use of this final thing. Now after that, this unit is going to react with your styrene unit, styrene molecule, uh, this way followed by the pen and the trans is due to the spheric reasons over here and the rest of the things can be really understand from this input. Now coming to this one, so this is quite related to that polymeric chain that we are uh, uh, having earlier. So had that long chain of polymer you can say. So if we hexene, so this small unit can be u- used and presence of the second generation plutonium is catalyst to this particular thing is leaves from the system and can reactive with small unit and normal cross metathesis should happen and give you this 11 extra this uh, ethinyl acetate with the Z ratio of it is to 20 around like this from 11 the ethinyl acetate with this for this conversion that graph is so that the omnivorous nuclear that we learn in the paste of apples, PRP test, and the this particular pheromone is in. 8:20 ratio, and the synthesis of this Whaler pheromone in particularly attractive target because of that proximity reduction in secondary drug therapy. So, this example of one of the total synthesis. So, here they have synthesized that this piperidine-based alkaloid, halosaline. So, that's natural way of doing molecule, and for that they have used this particular metathesis strategy. So, in this process, they able to do this cascade or domino RCMs in closing metathesis, opening metathesis, and followed by reclosing. So, this thing they able to do. Now, if we see the mechanism over here, so we have started with this kind of. So, at first, let's discuss in this cartoonic form, then the molecule we can change it. So, to have this kind of system, first, this one of them obviously going to be reacting with your Graphs catalyst, and you are going to generate this particular this particular resistance with. So in that you are going to generate this one. Now, closing metathesis should happen. So at first, this thing you have to and here you are going to have uh, kind of system, and in closing metathesis first step should happen like this. Here you have another step, this thing. So here if we see for these two rings actually, A and B, uh, from here to here if we consider, here we can see for this A cycle it is formed, it is a ring closing metathesis, but for that B rings it is the rings same, but here you can see that bond is broken up and it is open. So for according to B ring it is ring opening metathesis, and for A it is ring closing. So that's why these two is happening simultaneously. So each we need to form that A ring, so ring closing, that B ring must open, and that's why that RCM and ROF that two things occur one by one simultaneously. Now after that again, this thing would be happening like this way, and followed by again ring closing metaphysics. It will be these two rings, and that catalyst will be regenerated. This is the general strategy how they want to do RCM, ROM RCM, this particular tandem process for making this kind of food. For that, they have started with this particular acetate dictate alcohols, and so here it is reacted with this particular uh, Nile waste reagent like this. And here we have done, I think, some substitution reaction for making of this particular uh, thing. That first peptide can be formed on NGP process, you can say. That would occur then followed by this amine can be essentially to have that in the above. So after that, uh, same thing, very things. So now, let's consider it, clean this particular. If this kind of starting material that fast would be happening, followed by this, and this is the formation of. So, this influencing happens, where you have ring opening, it leads to formation of it. Yeah. We have that. Mm, again, this will be happening. Um, Let me write it here. That's right. Influencing metaphors your dream and you are generating in this way, studying feel generated following this particular study. Now, lastly, one of the example of that YM that in the ion method, so, this is for Deuterium distillation. And so in this particular reagent, first, it has two here. So, first, from forms with uh, is reacting with lithium and having kind of step. Then now the formation of this kind of system now in floating material which is happen in this two unit with something added this final elimination of because into the manipulation that it is in the different catalyst followed by this particular develop where the same right right this is so time type moiety yeah other resistance of this present that is the obviously there. So, it's kind of blue, movie. So, in my meditation, with lithium, we have done this one. Now, coming to the property, what we have, we have asked about earlier. So, uh, let's, uh, see. So, let's discuss this. Detail. So, we have this, strong, seen that some different kind of methods. So for that, when you get catalyst what are used are that metal carbide, right? So the mineral structure of metal carbide, so it remains in any of this kind of forms. So generally, it's clean that way it is considered active. So they are very reactive and transient species that metal carbide and their instability both kinetic and thermodynamic fluid obviously there and forms a strong bond with that kind of metal. So that actually gives little bit stabilization of your kind of carbon units as they are very much reactive and transit. So if by touching with metals, you can have some amount of stability. So this thing we just have seen already how metals work and what uh, uh, for polymers, we need to first with cracking presence of that kind of zirconium based reagent, this thing happen, then oligomerization and metathesis we can have this kind of thing with molybdenum based reagent, we can do that metathesis reaction. So here you can see that we are mapped to how this uh, catalyst has evolved. So initially in 1950, that sites are used for metathesis reaction, where helium, molybdenum, kind of metals, and in 2000 actually that graphs and Schwartz have discovered in 1990s. Schwartz have discovered that molybdenum based one, and for and 2000 graph develops the MHP based fixing it as explained for and about. So it's some at important synthesis catalysts that are used. So these are feature carbon low oxidation state and this tantalum based gas, higher oxidation state gas of carbon. So the differentiation that we find that these lithium based ones are example of this hybrid difference of carbon complexity is phenylenediamine contact. So as this particular group is there, so that it is called phenylenediamine and needs the is obviously there. And the nature is that carbon with the reaction. So one we have seen from Gen 1 and Gen 3, this one, and this is the field gender, which is that is the catalyst that when the graph and again the examples that are used the thing for page OP process in higher polishing process, how it's step of metathesis is the method R1 and R4 and 2 and 3 that we have described. And cross metathesis, for this one we have seen cross metathesis ring closing because this one actually was given ring opening metathesis polymerization. So when the ring opening happens over here and it got polymerized in this situation. So this is actually RO in and addition metathesis on here. So alkyne, so not only alkenes undergo this kind of process, it's the use alkyne you could say, and for alkyl ones we the same kind of that is can be used. 9 metathesis because in they generally make this kind of die-ins and one pot. So this step. So for including metathesis, so two pathways these are proposed pairwise and non-pairwise. So for this is one of the early proposals that it happens in this kind of manner. First, if activation is there, this is a non-pairwise, and then first one of the olefin is activated like this way, and then it would react with another and have this kind of system followed by that in opening here we can say briefly these two products. So this for FY1 and in that way uh, that can be generated. And so for pathway B, what is proposed that the metal carbon is missing used. So for that, two olefins are That's like this way. Metal actually is originating with four carbon center, and ultimately with can with that ring opening and would lead to monomer if leads to easy. So how they have proved that? So to, to prove this one, they have used this reaction. So 1,7 extra so we due to it with deuterium one and with proton one, these two variants they have used, and they have used this mm, uh, these two unit, and we have done the metaphysicians reaction. So what they have seen is they have seen generation of particular H2 unit and uh, these two these two, different units we have. So in this way actually they have proven uh, that they cannot be pairwise, but if that happens you are going to see it's kind of intermediate because all four centers that can react fast. So that's why if at time it can it should be not possible. In that way they have so ring opening again we have this price and this one again we discuss this coming to our reward question. So there they have asked asked that kind of polymerization is created. Premium one that's when to get like this. We have ring openings happening. Uh, this kind of system now that this can react with another sequencing unit. So you can say this or any small chain if it is given like this way and react and followed by only by one which is size which was uh, in elongation we can check and polymerization happens on this chemical. So it is called immunotherapy metaphysics followed by polymerization. Otherwise, it means you want to know about current for organic complex. But So for welcome, so this metal unit this nucleophilic energies nucleophilic they are that nucleophile can attach and can have uh, nucleophilic can do that nucleophilic value very negative negative. For the physicists, because of this thing, for here, instant release nucleophilic nucleic very so for this kind of cases, uh, these are electron donating atoms like oxygen, nitrogen, sulfur. These are maybe electron load very there, so that can have stability and say here it is with more positive charge is here. This is electron. For these cases, they are normal alkyl chains alkyl chain unit for hydrogen. So let's say that here this inverse very good. For the thickness cases, they are the metals are high fillet shine now and they are actually low valence on the children which comes in and this time. Now if we compare that if we talk about thin and NHP, NHP are better sigma donors and the base sigma donor that are present are NHP in terms of sigma donation it is better. So reactivity is mixed. NHP hydrolyzation rapidly but trial phosphine are not very good. So we have basically the reactivity increases and have to learn the thing. And when it is reactivity oxygen, it is the not react with oxygen and requires special reagent for oxidation but for phosphine, they are reactive with what? If we see the valves, so it is generally very that and phosphine we can reach multiple phosphine only metallic bonds can be considered again in uh, very strong bond stronger bond and they are not really dismissible but for phosphine it can be dismissed really easily. So for business for fixer singlet carbon so here they are this gas with singlet state. And if we see that connectivity with the metal, it has this kind of sigma donation and phi contains this kind of properties so that this kind of sparking got ability to increase sigma donation and phi activity. And phi donor substituents such with okay, so oxygen and nitrogen don't very serious at all. And reduce fractionation from this. So, so that's Fisher carbon. This is here. And for carbon, it is split. So it have this kind of shape and that they are actually highly charged mm, metals very different, like tantalum. And if we see the differences, so sigma donor and singlet carbene, they are triplet carbene and two covalent bonds. So for this, we consider one sigma one, right? And he has two covalent bonds. Um, yeah, it forms as a triplet set. So that's it. It's like this. So here three orbitals are three structures, but here in the triplet state, the unpaired electrons are there. So this uh, picking up like this thing, and same way, in the same. This is for your self-confidence. So you are by cells and the free carbene and the uh, molecular orbital, which will have more hidden character than metal. The loop one and homo have more metal character than silicate. This is the energy difference, and in that way it is explained for each let me each part. Uh, Here it is having more different characters. So the opposite of the carbon. So here carbon cell carbon electron deficient carbons are and stabilized by heteroatom or small with metabolite nucleophile. Throughout where electron is destabilized by uh, heteroatom. The heteroatom is there stability is less and affected by nucleophile. So for metal, they are generally low oxidation state, electron rich, usually D6 is in electron elements and atomic electron size electron rich and stabilized by electron field because of electron distribution so that it can this can stabilize that electron that will be stabilized. So for this kind of soft carbons, metal are in high oxidation state, electron deficient, so they are generally toward nuclear system, 16, 14, this kind of electron. And they are attacked by nucleophile and electron donating ligands can stabilize them, but 15 electron won't heal, so they are deficient. If your ligand have electron that can donate and stabilize that non-metal. So here, this in double bond, this metal carbon bond, it is relatively weak, and the area of rotation is lower because here you are thinking, uh, they are actually nitrogen or oxygen. So this kind of thing happens. So it have uh, self single bond pressure. So that's why bond is weak and rotational barrier is less. And for kind of for carbons, they are strong because they are normal melting units are there. So electron cannot push like this, and so they are always having this kind of system and double bond kind of character. So their rotational area of rotation is higher. Okay, fine. And coming to this, now we see the available options. So self-charging complex the oil for carbon are different in nature. So this proceed because here. For social carbon, your carbon center is going to be placed by nucleophiles. So they are electron. Okay. Not correct. Definitely. Social carbon, carbon divided that sigma donor and strong five except that five slots again we had left on this uh, sigma donor. Here, not carbon ligand that carbon atom we check that sigma donor not your not your ligand, not correct. And methyl carbon that carbon bond is very feature that they have got to very fast to short carbon and metal carbon bond is stronger because it is alkene, so no single one character is there and it has high area of rotation. So now the carbon ligand in sister carbon is singlet and soft carbon is carbon these. So Solomon they want to the right option. So the uh, first generation catalyst. So that is uh, this one is used for this field for catalyst. So I molybdenum is kind of things there. Which second generation catalyst is uh, this fourth you know, uh, is catalyst. Now is uh, new catalyst these three are it. This part we have already discussed in detail. Now, alkene which can so that reopening uh reopening polymerization metaphysics reopening metaphysics polymerization that it drug gen 1 catalyst is that mm, these types low and uh if we without accept this as low in addition I think now coming to this one let's do the discussion about LHD so they're not uh, we just we have seen the properties so they do not easily react with then they need couple of places then this is correct metal can longer comparison to right not hydrolyzed with but longer so yeah first for us yeah that is carbons they do not react easily, but for carbons, they easily, yeah, not. But X is what it means here bitter. Now, because in what was carbon, of carbon. So they are lower, not higher of question. Carbon filter is locally measure of higher, right? These and coming to these, so this is a not carbon. We have learned that, and here is the very high kind of instead of this. And I mean, it will be pretty much there. So 150 so 5 so it is this kind of thing. That's why 5 plus this is there. So this so I think this last question can number per video. And now if you have any question you can ask, you can finish this section. If fine then we can close. So next Friday we can continue our discussion. So we can thank you all for joining our small time. Okay, now. Again, thank you for joining.